We are familiar with the rich and wondrous star field in the night skies, or at least we were in the days before light pollution in our major cities. On the right of your screen, you see one of the glorious images of the universe taken from the Hubble Space Telescope. The stars form pinpricks in space, scattered richly, thickly, and sometimes sparsely. How are the stars distributed in space? An approach to modeling is suggested by a consideration of the Poisson process. Now, the listener will recall that we constructed the Poisson process with an arrival process in mind. There was time's arrow going to the right, and arrivals arrived at random points in time. But if she will go back and look at the way we define the process, she will discover that time's arrow and the direction of time was in no wise critical to the way we defined a probability model to try to capture this kind of arrival process. And indeed, the basic definition of the Poisson process could just as well have been made in space instead of time. And so we could deal in space with a spatial Poisson process in 1 dimension or 2 dimensions or 3 dimensions. For definiteness, let's talk about 3 dimensions, though naturally questions of volume in 3 dimensions become area in 2 and become length in 1. So what we want to do is find a proper abstraction of the model of a Poisson process to capture a spatial process where points in space now, connoting the arrivals in time, but of course arrivals is not the proper word anymore, we're dealing with space. We'll call these points in space Poisson points. Poisson points appear at a mean intensity of alpha points per unit volume. In 2 dimensions, it'll be alpha points per unit area, and 1 alpha points per unit length. What should then characterize the probability distribution for the process? Well, naturally enough, we begin by considering regions in space. Let's say we consider some region denoted abstractly by A. A key element in the definition of the Poisson process is that the number of Poisson points in A should in no wise depend upon the particular geometric features of A, but should depend solely upon the volume of A. Replace volume, of course, by area or length if you have 2 or 1 dimensions. So we require that in any region A, whose volume is, say, V, the number of Poisson points is chance-driven in that region, and that number is governed by a Poisson distribution with a parameter alpha times V. Another way of saying this is, if you have a region of volume V, the expected number of Poisson points in it should be alpha times V. Of course, this corresponds to a mean arrival rate of alpha per unit volume. Well, of course, this is not going to be enough, right? This gives us a Poisson structure. But once we have such a structure, this gives us something analogous to the independent increment property. To wit, if one now looks at disjoint, non-overlapping regions in space, each of them, per our basic assumption, is going to have a Poisson distributed number of points. The number of points across these disjoint regions must be independent trials. And there you have it. We now have a spatial Poisson process in 1, 2, or 3 dimensions. Such processes are important in modeling random scatter in space. Of course, we could imagine using such a process to model the number of stars in a galaxy or a certain quadrant in the night sky. We can use such processes in 2 dimensions to model noise in images. For example, if the listener has ever seen an ultrasound image, she will remark on how noisy and grainy it appears. You'll see an image, and in the image you'll find specular points of light here and there and thither. And a characterization of these deformities, if you will, these imperfections, is provided by a 2-dimensional Poisson process. Noise processes in 2 dimensions are usually called speckle, and Poisson processes in two dimensions provide natural avenues to characterize speckle or noise in such images. The listener should always bear in mind, when applying a mathematical model to a physical setting, as to whether the model's assumptions actually are in consonance with the physical reality. So let's go back to the distribution of star fields and ask, how good is it that a Poisson spatial process should be used as a model for such a system? At heart here is the idea that we're treating Poisson points as literal points in space. But of course, the listener could object and say, well, a star is a rather massive object, is it not? The key here is to understand that, yes, a star is a large object using earthly standards of distance, but on a stellar scale, it is actually a rather small object, and in the vast depths of interstellar space, it could easily be viewed as being approximated as a point in space. In other words, we eschew formally the possibilities of double stars, triple stars. No, stars are simple, singular point objects. What about the independence characterization? Right, again, a listener might object and saying, well, look, we require that regions which are disjoint have independent star formation processes. But surely, if you have two regions right next to each other, and you have star formation close to the periphery of these regions, then surely there will be gravitational interactions. And again, the answer here would be to consider the immensity of space. Perhaps the right way to think about this is to think of units in space, not in terms of, let's say, meters or kilometers even, but in terms of, say, stellar dimensions as units of dimension, or perhaps even better, galaxy-wide dimensions, or perhaps even parsecs, 1 light year aside, as a unit of interstellar space. At such dimensions, gravitation plays a very, very small role because of the inverse square law. And therefore, again, one might have a reasonable guess that an independence assumption might not be too draconian an assumption in such a setting. As always, the reader should always check the bona fides of the mathematical model in the particular physical circumstance.